I think we have to start. So let me ask the committee first. Do you want to discuss this, or we start with the presentation and then we discuss? Sure. All right.
Well, hello everyone. Thanks for making it to my presentation of my PhD defense. My committee members are committee chair is Dr. Principe, my advisor. Members are Dr. Harris and Dr. Hammer from our department, and our external member is Dr. Sain from the Department of Music. The title of my talk will be Self-Organized Computational Perception in Time-Frequency Domain. So this is how the talk will go. We will first give a brief introduction of the field, related work, then we will introduce our model, nested hierarchical linear dynamical system. We will discuss the formal properties of the model and show an interesting application that relates to music theory as an outcome of these formal properties. Finally, we will give some classification results on monophonic and polyphonic notes. So what are the common machine learning signal processing tools that are used in the literature for music information retrieval? Pretty much anything that you can think that has been done in the field of machine learning and statistical signal processing has been applied, because these are tools in our artillery, and they have now a new problem came ahead, and they decided to apply them one by one. So from statistical tools to wavelets to neural networks, base classifiers, decision trees, anything you can think of has been applied to various tasks. The simple tasks are pitch estimation, chord classification, which leads to automatic music transcription. And there is more complex tasks such as recommender systems, music emotion annotation, music segmentation, and genre classification. So conventionally, we use classifiers or clustering algorithms to extract structure from the data whenever we see that there's structure. Welcome. We started just a second ago. Okay, sorry. And we know that as a framework, classification assumes a static environment. However, this may not be true, because most of the real-world signals are created through dynamical processes, and they have temporal information. So what are the static models? A few examples. Most of the clustering models, such as k-means, mean shift, GMMs, and then we have neural network models such as multilayer perceptrons or support vector machines, are static models. What do? Is they model the probability density of the observations. They essentially follow a bag of feature vectors approach, so they do not care in which order the features are presented to the model. So they don't use the temporal information. On the other hand, we have dynamical models, which we will talk about two of them very briefly. HMMs, hidden Markov models, are generalized mixture models. They are generative models of data. They model the time evolution of observation sequences, assuming a Markov process, but they have a discrete state space. On the other hand, linear or nonlinear dynamical systems are also generative models of data. They intrinsically model time evolution of systems, but they have continuous state spaces which can create continuous representation spaces. And through the use of inference, they can deal with non-stationarity of the signals. So the question we will try to answer throughout this talk is, can we use a dynamical system which is not trained to be discriminative to do classification, a discriminative task? So what is the related work in the field? Dynamic textures are linear dynamical models, and they have been extensively applied to especially higher semantic tasks such as genre classification or music segmentation. They are linear, but they're usually implemented in mixture models. So hundreds or thousands of these models in parallel are trained on a segment or on a piece of audio, and they do specialize in certain segments of this time signal. So this high number of models increases the computational cost of the overall approach. On the other hand, we have nonlinear models such as Hopfield networks or recursive neural nets, deep networks. They come with many appealing properties, which separability, sparsity, and generalization are just a few of those. However, to achieve these, they have very complex cost functions, usually with complicated constraints on the cost. So they have high computational cost. Munkong and Zhuang, famous names in speech processing, suggested a paradigm called constructionist paradigm that essentially suggests building models for auditory perception such that at each layer, these models will solve a critical task, and then these layers interact with each other, and as they go higher up in the hierarchy, they start solving more complicated tasks. So our goal is to build such a building block solving certain tasks at each level, and hopefully doing it with a reasonable computational cost while getting some of these appealing properties. So to do this, let's consider a linear dynamical system. where here X are the hidden states of the model, Y are the observation signals that we get from the data, U are the input signals. So in this framework, I can use the input signals to drive the states to exhibit a certain desired property. This is the idea of, simple idea behind the controls. And given a set of input signals and observations, I can use the Kalman filter to infer the hidden states of the model. But what if I want the model to exhibit a certain behavior, but I do not have any specific input signal that I can feed this model? So I want this to be unsupervised. So then I need a constraint dynamics that could be used for discrimination, that can potentially lead to clustering. So to do this, we came up with a new organization architecture where I have a single layer of measurement equation and multiple layers of hidden state transition equations. Only the first layer of the states directly relate to the observations. However, all the rest of the layers act as inputs that drive the layer below them. And on the top layer, we enforce a constraint such that the states exhibit a Brownian motion. So this topological constraint creates clusters in the highest state space of the model, resembling the Hopfield's idea of attractors in the energy space of the neural network, and makes the neural network driven bottom up by the inference and top down by the topological constraints. And this mimics the active perception that takes place in the brain. We can, knowing that this is a linear model, and a cascaded set of linear models can be written as a bigger linear model, single linear model, we can rewrite the equation such that we have a joint state space and this particular state transition equation. What this tells me that I can actually use the Kalman filter equations to jointly estimate the states in this space. But what is interesting is now through our topological constraints, through architecture design, we essentially created constraints on the parameters that would take very complicated additions to the cost function. But we can still use the unconstrained cost function to do the inference. So we keep the computational efficiency. So how do we do the parameter learning? We want to infer the states of the model and learn the parameters simultaneously. This is done using a framework called sequential estimation. It is an expectation maximization type of algorithm. The idea behind it is you switch the roles of parameters and the states and create this concatenated. You take the rows of parameters, concatenate them into a state vector, and assume identity transition over them. This, though, usually suffers from high dimensionality, because if I have a 60 by 60 transition matrix, then I have 3600 long state vector for the parameter estimation. So what people do is they neglect the second order statistics. But given that I do have a linear output model, I can actually observe that this observation in the output vector is created by the inner product of the state vector and the given row of the matrix. So this tells me that I can learn the rows of the parameters independently from each other. And while doing so, I come up with models that are much smaller in dimensionality. So here, I change the rows. I take the state vector and make it my measurement model. And the parameters are the corresponding row of the matrix. And I assume a Brownian motion of the state transitions. And I can use Kalman filter and propagate my second order statistics. And I do not lose any optimality while doing so. So what is the experimental setup that I will be using throughout this presentation? We want to use filters similar to cochlear filters. And gamma tone filters have been shown in the literature as viable models for cochlear filters. Also in the work of Levitsky in 2005, he has done sparse coding on audio signals and shown that the basis functions that are created through this optimization resembles the gamma tones filters, further increasing the viability of cochlear gamma tones as cochlear filter models. So we use fourth order filters and place them in the range of 10 Hertz to Nyquist frequency. And we place them an equivalent rectangular bandwidth away, half an equivalent rectangular bandwidth away from each other. This is also a commonly used framework for placing these filters. So, and more detailed explanation is in the thesis. And this is a pretty standard, so I don't want to go deeper into it. Our observation sequences will be single-sided magnitude spectrums of the signal. The audio signal will be windowed using a symmetric L-point Henning window. And the windows will be selected such that I have about 70 to 80 milliseconds of data. Windows will have 50% of an overlap. So how can I learn isolated instrument notes or chords. In the experiments, we will use the audio samples from the University of Iowa Musical Instrument Samples dataset. The recordings are originally 44.1 kilohertz, and I downsampled them to 11K. I use 1024 point FFT, so this makes my observation vector a length of 512. And through the placement of my cochlear filters, the first layer dimensionality is always 60 dimensions. We use, as I said, sequential estimation to learn the parameters. Once the parameters are learned, we fix the parameters. So once the learning process is done, the model is not adaptive anymore, but further training can be done if is needed. An interesting side note here is that we will explain that this model can discover patterns given a set of training samples, training sequences. So we do not need to choose the number of clusters a priori, which is very interesting because most of the clustering algorithms do require the cluster number to be chosen. So when we talk about convergence throughout this work, we developed a very simple convergence criteria. We keep a window of node assignments in our memory. And if this node assignment is not unanimous, for instance, here it was C4, and now I decided to label it G#3, then I say a change has happened. So I start labeling my outputs. And wait till my memory has unanimous decision. And once that happens, I declare convergence. I say I'm in the neighborhood of a cluster for 4 time units. And then I can go back if I want and correct my decisions since the change till that point. This is a very simple idea, which comes with negligible computational cost and a small lag in the real-time operation. And these experiments, I use a window depth of 4 windows. But I also show preliminary results on other solutions, which I think is necessary to improve the results.
Oh, just one point.
Yes.
So I tell my students that they should always think like their algorithm. But now when you are explaining things that the system is doing, you say, I don't. All right.
So the model continuously does these processes and keeps a window of memory as node assignments. Okay. So what are the formal properties of the model? So we can study these through the impulse and steady-state responses, as these properties depend on the parameters that are learned. And for the sake of simplicity, for the rest of the study of this section, I will ignore the noise uncertainties in the equations. So the first thing to look is the stability of the model. When I do the sequential estimation, a commonly known problem is a degenerate solution where the parameters diverge and states converge to 0. So to avoid this, at each iteration, we force the columns of the parameter matrices to have unit norm. And if I say the spectral radius of f is given by rho of f, which is the largest eigenvalue of the matrix, and x lambda is the corresponding eigenvector, I can write these equality. This is the largest lambda. I can bring it into the norm, use the eigenvalue property, and then this tells me that when I look at this inequality, the largest eigenvalue of the matrix is actually bounded by any induced matrix norm. And given that I normalize the columns of the model to be 1, this is actually an induced matrix norm. So this tells my eigenvalues will always be less than 1, which ensures the stability of the model. The top-down steady-state response can be written by as follows with these summations. But given the eigenvalues are less than 1, I can actually come up with this closed-form solution. What this tells me is that the top layer states actually embed a small subspace into the observation. So given an observation, I have a reachable subspace in the top layer, in the small subspace, that my states exist. So this is the property that we are taking advantage of to do the clustering. Given a steady set of parameters, features, I can go into this subspace in the smaller space. And this is still a continuous space, so I do take advantage of an infinite number of possibilities to place these clusters to. Similarly, the impulse response can be written as these terms. One interesting thing here is to look at is this t-2, which this one is given by the depth of our model. In our experiments, I have used 3 layers, which was heuristically chosen. But I have results on using 2 layers, and this is the minimum number of layers because I want that constraint layer on the top. And If I use 2 layers, this would be t minus 1. If I use 4 layers, this would be t minus 3. So this tells me that if I increase the number of layers in this model, I basically create a temporal depth. And this is something we also, as I was mentioned, that we want to study in the future. So we have these closed form solutions, but the parameters change for each application at each training. So we want to experimentally study the properties of the model, and we want to start with the convergence time of the model. When we do this, we see that the model usually takes about 250 to 400 milliseconds to make a decision. This is biologically plausible because latencies as long as half a second have been shown on the cortex of behaving monkeys after an auditory stimulus. But even though this is biologically plausible, this costs me classification accuracy. So we want to look into this in a little more detail. Here, I took a single model of dimensionalities 3, 10, and 60, top layer, middle layer, and observation layer. And I looked at the convergence times using my convergence criteria between each cluster. And I see that, as I said, about 10 windows is most of my convergence happens, and that is 400 milliseconds. I have these other ones that are because of the clusters that are further away, and they take a longer time to converge. But this was one study, and we wanted to see if, in general, this is a similar distribution. So I took 51 models. They all have at least 80% classification accuracy for all time instances without using the convergence criteria. So I know these models have good separability. The models have all different dimensionalities between 3 states to 12 states on the top layer and 10 to 25 in the middle layer. And I look at the distribution of convergence times for about 5,700 transitions. Here, I also implement a linear winner-take-all model where each unit, there's n units for n clusters, and the input layer for the units are the cluster coordinates. And each unit gives a negative feedback to the other units and has a self-positive feedback. I see that our convergence criteria peaks around 4 windows, and on average takes about 8 windows to make a decision, while the winner-take-all network takes about 6 windows to make a decision. But further interesting is our mode now is 2 and 3, somewhere between 2 and 3, which means within about 100 milliseconds, this model usually makes a decision. So this is a great improvement. Rest of the results, I still use my convergence criteria, but this is something that I want to implement in the upcoming publications, hopefully. But to further reduce the problem of convergence times, Carlos helped me develop, he did most of the work on the time domain implementation of the HLDS. So instead of using the gamma tones in my measurement model as frequency masks, now we have gamma tone filter bank, time domain filter bank. And I pass my input signal. Now at the output of these filters, of course, I have oscillating signals. So, and oscillations I know through a linear model will create oscillations on the top layer. And to reduce this, we want to estimate sort of the power of each output. So we use a recursive mean estimation at the output of the filter bank and feed the output of the mean estimators to the HLDS using the identity measurement model. Here I show the performance of the model in classification of isolated trumpet notes, and for a different number of dimensionalities. And I see that we get as good as 98% classification accuracy. In the parentheses are the performance of the frequency domain implementation with the same dimensionality. And we show that we can improve the results as much as 4.5% using this convergence time. And the reason is, here I show the histogram of convergence times, and I can see that most of the convergence happens within 400 samples. That is actually about 40 milliseconds of data. So within 50 milliseconds, I do declare convergence using this model. And this translates to about 4% improvement in the accuracy. Next thing we want to study is the effect of the noise parameters. So to do this, I have 2 noise parameters. One is for the state transition equations, and one is for the measurement equations. To study each of them, we fix the other one, and then we vary the one of interest from 0.1 to 25. I do this for 4 different models of different dimensionalities, 3 and 10, 5 and 10, 8, 20, and 12, 20. So intuitively, I expected when I do this for the state transition equations to have an increasing line, because our intuition was that the model takes a long time to converge, and then if we increase the state transition parameter value, states will move faster, and I will have higher classification accuracy. But this wasn't the case, and in the next slide I'll explain why. But this behavior was expected because we already have a model that is not overcomplete. We have 512 dimensions in the observations and 60 dimensions in the first stage. So we already are estimating the observations with a given error. So increasing this error number within this range does not reduce my performance significantly, but has other effects on the distribution and self-organization of the model, which will I explain now. We realized that if I increase the noise parameter value in the measurement equation, the representation space actually shrinks. And the idea is similar to compression. If I want lossless compression, I need more data. So my representation space has to grow to support this detail needed to do the perfect estimation of the observations, as good as the model can. And inversely, if I reduce the value of these parameters, they grow. If I increase, they shrink. The state space parameter, in return, if I increase the parameter, the space actually grows. And this makes sense because states now can move freely and faster. But we realized that the cluster radiuses also grow in the same ratio. So now I have these clusters being spread with higher values of the state transition equation noise, but now the clusters are also bigger. So the classification accuracy overall did not change. So what is the best strategy in choosing these parameters? Our idea is to choose low values for both. When I choose low values for the measurement equation, I know that the clusters spread apart. When I choose low values for the state transition equation, I know the cluster radius shrink, so this increases the separability. And this is exactly what we do for the parameters in the rest of the results. Here, I show the effect of second and third layer dimensionalities of the model on classification accuracy. These are obtained by isolated trumpet nodes, and these are obtained by chords, isolated chords that are created by using trumpet nodes in my data set. In both cases, I see that model dimensions of 520 gives the best results, which is very close to dimensionalities of 310 and 414, both in monophonic and polyphonic cases. So I know that the model usually behaves the best when it has the top layer dimensionality of 3 to 5 dimensions. I have seen that the clusters actually are formed in large models, but it takes a longer time for the model to converge, hence reducing the average performance as well as the best performance. We see that 72% and 82% in these cases are the worst performances. And this is something to study further to see how can we solve this convergence rate problem. The average results are usually lower than the best result, of course, but there is a significant change most of the time because the standard deviations are 10 to as large as 18% in the worst cases. And this is due to the local minimum. When I do the EM type algorithms, I do have local minimums in the sequential estimation. And even though these parameters solve the problem of estimating the observations, they do not essentially create organizations that we benefit from. So what is the self-organization of HLDS is like? To get a feel of that, first I want to mention that as we use gamma tone filters, we essentially are using nonlinear masks on the frequency domain. And I'm fitting these nonlinear masks onto the observation data using linear inference. So this inference on nonlinear masks plus the hierarchical structure of reducing dimensionalities form the essence of my self-organization. To see the behavior of self-organization without the inference, I create a top-down reconstruction of a given cluster, and I propagate this cluster center through the input matrices in my model. And that is the blue line that I show here. And the dashed red line is the observation that corresponds to that cluster that I have not used while creating the blue line. I see that the model, even without the inference, captured the prominent peaks in the data while suppressing the neighborhoods of the prominent peaks. So we believe that this model was able to capture the harmonic structure of the data, so the frequency landscape, and learn this metric to self-organize itself. So to look further into these areas, this actually resembles the surround inhibition in the brain, which in the literature, people have used nonlinear models to create this type of behavior. Here, to test this phenomena, I created a test observation with a single peak in the frequency domain, and then I run inference on the model. I see that the model chose the filter with the closest center frequency and activated it. But then, as it has a broad selectivity in the frequency domain, which is a property of the gamma tones, it compensates through the use of inference by negatively activating the neighboring filters. And in return, when I sum up the response of the filter, which is this black line, I see these little dips that suppress the neighboring areas around the peak that resemble surround inhibition. So if I also look into the state transition matrix, I see that most of the states negative feedback to the neighboring states, and it is learned through this compensation through inference because of the broad selectivity of gamma tones. So we noticed that our model actually can, as I said, discover patterns. So to test this, we trained the model using 34 of the 35 nodes in my data set. And then first, in a generalization framework, I want to see what would the model label this pattern as, this new pattern as, which it has never seen before. And 50% of the time, I noticed that the model chooses other octaves of the same note or perfect fifths of it. So in this case of C, it chooses either G, F, or other Cs, C4 or C6 in my data set. So this makes sense in a generalization framework because it fails, of course, because it has never seen this pattern, but it chooses the most related. Most of the time, it chooses something that's related musically to the signal itself. But when I presented these signals to the model, I actually saw that they have their own clusters. So in this case, I showed, okay. In this case, I have actually trained the model without F#3. And then I presented that F#3 to the model and see that it has a cluster that is placed here. And here, C# is, I think, related as a perfect fit to F#. And I can see all the C# are within the proximity of my cluster. So this supports the selection that I have not mentioned here. Similarly for B5, B5 was not in the training, and the cluster is actually placed somewhere close to B4. It's something that is musically related to itself. So we hypothesized that this model can actually learn the metric of the musical space, the harmonic structure of the data. So to study this in a generalization framework, we train 7 models, leaving each of the 35 nodes out, creating a total of 245 models. Almost 180 of these models actually end up having more than 90% classification accuracy. And here I show the PDFs of these 2 tests. Blue line is obtained with training on all the nodes. Red line is obtained by training on 34 out of 35. And assuming I have a cluster, so I use the idea that I have a cluster for that node as well, I discovered that node to do the classification. And I see that the PDFs are pretty similar, and we test the null hypothesis that the means are equal using 2 sample t-tests, and the p-value is not enough to reject this hypothesis. So we deduced that the model was able to generalize quite successfully. But now, if I have learned the harmonic structure of musical notes, can I actually train the model on trumpet and learn it to classify another instrument? And that is exactly what we tried. We trained the system on trumpet notes and tested on saxophone notes. We used the discovery property of the HLDS and find the clusters that correspond to each of the saxophone notes, and see that the model that had a 90% classification accuracy on trumpet notes has about 82% accuracy in the saxophone notes. So it still had separability. It had a lower performance, which I think is related to the fine-tuning of the model, because even though the harmonics are in the same places, their weights have changed, moving from one instrument to the other. So the model is in some parts of the space that it has not seen before. And with a little more training, I think this model's performance will go up to the level of the trumpet. So there's a concept that's called musical distance. And this is a concept that is created by music theorists. And it is a top-down concept. They do know the properties of how the musical notes react, how they interact with each other, and they came up with these concepts. But can we actually ground these concepts to musical data, to physical signals, using the modeling approach? So we need a representation space that's created by a modeling technique, and see if it exhibits similar properties declared by the music theoretic concepts. So what are the 2 music distance concepts we will study in this work? One of them is the distance that is declared by voice leading spaces. So voice leading spaces basically say that two musical notes are related to each other. They're close to each other. If they're close to each other on the piano keyboard, so C and B is close to each other in the space. So we can just use the metric on the reals. But if I ignore the octave information, now I can take this linear organization and fold it into a circle, which gives me the circular organization. And here again, the C and B is the closest notes. So now finding a distance between two notes is as simple as counting how many steps it takes to move from one circle to the other. This can be generalized to chords by finding the minimum movement needed to move the circles from one chord's members to the next chord's members. So here I see that from a chord that is consisted of C, E, and G to C, D sharp, and G, I just need a movement of 1 unit, and that is the voice leading distance between these two chords. The second concept of music distance is based on acoustics, and it defines a relationship that's harmonically rooted. And they visualize this distance in these shapes that are called tonetses. Here, each note is a musical note, and each line declares a certain relationship between these notes. The horizontal lines are the perfect fifths, and the diagonals are major and minor thirds. Here they generalize it to the case of chords. Capital letters are actually major chords, and the lowercase letters are minor chords. And here I see, for instance, that the C major chord is related to C minor, E minor, and A minor based on this harmonic relationship. And most of the time, in this organization, if two chords have more common members, they are closer because they have more harmonic similarity. So as I reduce the dimensionality, while I go higher in the hierarchy in my model, I essentially tell the model to activate a set of states in its lower layers with the same state in the up layer, top layers. So this hopefully and essentially does create an effect where I can activate the same harmonics with the same input state from the top layer. And this would resemble the organization of Riemannian tonics, because then I will be choosing the harmonics simultaneously using a single state on the top layer. And also, as I use gamma tones in the measurement model, I have, as I said, I have this broad selectivity in frequency domain. So essentially, I might be grouping notes that have close fundamental frequencies together in my representation space. So we will see which of these is more prominent when studied within the framework of HLDS. We trained models on isolated trumpet notes, and we have looked at the neighbors of C5, and we see that 86% of the time, F is within the top 10 neighbors of this note. Similarly, C, G, D sharp, and E are at least 50% of the time within the top 10 neighbors of my musical note. And if I look at the relationship of these notes to the musical note C, I see that they're either perfect fifths, minor thirds, major thirds, or another octave. So I see that in the monophonic case, model have placed musical notes that are harmonically related closer to my cluster center. In the polyphonic case, we see a similar behavior where the model actually chooses chords that have more common members and places them closer in my representation space. I have many tables in my dissertation, but I didn't want to clutter these. So they are actually in there, and I show statistical study. I train tens of models and show an average performance on the neighborhoods. But if I look at the global organization of my representation space, here I look at the C major chord, and I look at all the chords in my representation space, and I order them based on the distance on my representation space. So 0 is the chord itself, 1 is the closest cluster to the cluster of interest, and so on. And I measure the voice leading distance between this chord and the corresponding chord. And I see that on average, the voice leading distance increases as I go further away in my representation space. This is not a surprise because the Riemannian organization, Thomas organization, also supports the voice leading organization. These are not essentially the same things, but they do not highly contradict each other. And Timotitko has a paper where he actually studies the similarities between these music theoretic concepts. But I want to see the behavior of HLDS where these two models disagree. So for instance, in the Riemannian tonettes, C major chord is closer to F major, And in the voice leading spaces, C major is closer to F minor compared to F major. So I see that in 10 out of 15 cases, my model behaves like the Riemannian tonets, which is a harmonically organized distance matrix, and places C major closer to F major. Using the experimental setups I've explained, I do monophonic note classification on 11 different instruments using the Iowa data set. I compare my results to swipe and yin. Yin is the most commonly used algorithm in terms of monophonic pitch estimation. Swipe is developed by Camacho, Dr. Harris's previous students. And it's actually, on average, has a better performance compared to yin, but it's not as widespread yet. So hopefully it catches on and it becomes the standard. I see that HLDS outperforms both of the models in 10 out of the 11 cases, except tenor trombone, where swipe actually outperformed us, but we are within 0.16% of the best performing algorithm. Whenever these models had a free parameter, we optimized it using a scan over the parameter space, and we report the best performance for each of the models. To test this in a more realistic setup, rather than isolated note classification, we created the song Yesterday by the Beatles, and then used each of these algorithms to transcribe the music piece. And then we see that HLDS outperforms the other methods by 1 or 2%. To extend this work to chord classification, we will only limit the study to triads, and then this will be minors, majors, augmented triads, and diminished triads. Given 35 notes in my data set of trumpet recordings, this ends up giving me 112 time series for these triads. I compare my method to the work proposed by Vincent et al. It basically uses a non-negative constrained non-negative matrix factorization. I chose this model to compare against because it is essentially my measurement model without any dynamics. And the big difference is they have an overcomplete state space model. So their state dimensionality is larger than the observation dimensionality. The code is made available by the authors, and I optimize the free parameters again by doing a scan over the range of possible values. And we see that HLDS is successfully classifying 93.45% of the chords, while NMF-based algorithm was about 91.45%. So we outperform it with 2%. So, in conclusion, here we introduced a new model consisting of a linear dynamical system with a topological constraint. In our experiments, we have shown that this model can create clusters in its representation space, and we have successfully used these clusters to do node or chord classification and shown improvement on top of the state of the art. We demonstrate the generalization and discovery properties of the HLDS, analyze its self-organization, and relate it to music theoretic concepts of musical distance, and show that our model favors the organization of the Riemannian tonets, the harmonic relationship, over the voice leading relationship. We analyzed the convergence time of the model and introduced the time domain implementation as an improvement. And as we use a linear model, and as we use just a single model to do this task, the computational cost was very reasonable. In the new servers we got, we can actually train this model in real time. And in our regular computers, we can run this algorithm in real time. So this is a big improvement on the competing methods as well. So when we started, our goal was saying, can we create a linear computational efficient model and obtain some interesting behavior that we see with these more complicated models? And I hope I was able to convey that we created a linear model that is topologically constrained, so I can use my unconstrained cost function to do the inference, and I can work in real time to do classification, a discriminative task, and come up with the generalizing and self-organizing model that can relate to interesting music theoretic concepts as well. So as part of future work, we want to study the layered organization of the HLDS. As I said, models with 2 layers are possible to train, and I have trained them. And on average, they perform better. So maybe for a classification task, 2-layer is better. But my intuition is for harder semantic concepts as segmentation or emotion annotation. I don't know if we can get this model to emotion annotation, but we might need a higher temporal depth, which means we need higher number of layers. So this is something to study and analyze. Can we build hierarchies using this basic building block to extend this work to higher semantic musical concepts? So we did the note and chord classification using this model. can we actually extend this work in the hierarchy of Western music to motives? And we know that given a set of motives and notes, these make up themes in these musical pieces. So can I stack these models on top of each other and possibly extend this work first to motive, and then the note classification and motive classification working in sync, resembling the constructionist paradigm that I explained in the beginning? Can they solve the harder question of classifying themes in the music pieces? So this is something that we want to explore and see if it is a possibility. And Pedro in Portugal might be taking the first steps in this path and try to see if we can use this model to classify motives. When we take this task to this uncharted territory, for our case, it's charted for the other works, we might need to introduce sparsity into model, because we have seen going from monophonic to polyphonic, we took the number of time series from 35 to 112. And that was only by constraining the work to 3x. So if I start considering all type of possible chords, maybe up till 7th, and then taking it to motives, I have an incredible number of features and patterns that I need to classify. So sparsity might be a useful tool in this case to keep the memory of the model from forgetting what it has learned before. But this can be done in caution, because sparsity usually creates a lot of computational cost. So what are clever ways of doing this while getting a behavior that's close to sparsity and keeping our computational efficiency is a question. As I said, my decision-making criteria of the convergence is very simple, very just intuitive and basic. And we have shown that the winner-take-all network, still a basic linear model, can improve upon it. So maybe using map decision rules or even further complicated decision rules can improve the classification accuracy of this work. These are the publications that I have published or hopefully will publish within this work. We just submitted these 2 journal papers, and I have authored or co-authored 9 conference papers. 8 of them are accepted or published, 1 of them is waiting evaluation. And we submitted the patent on adaptive background estimation, the 2nd year of my work. So thank you. I hope I wasn't too over time. And any questions, I would like to appreciate it. And I just want to put this background from 2010 to yesterday. So we have had a lot of good memories.
Now I understand why when Matt was not very responsive this morning, you left him.
We shook him.
Around. So I asked him a question and they mumbled, so now I understand.
And we had online viewers, Luis and Miguel, so I will see if they have questions as well.
Yeah,
seems like we have 8 viewers, but some of them are my family members. Guys, if you have any questions, please post them. There's a lag. So while we discuss, you can post your questions and I'll try to answer them. All right, so is there any questions?
This is going to the next level. This defense is now worldwide.
I didn't say it.
It's a YouTube live stream though, so we do not see them. That's one way.
All right, so let's start with the questions from the committee. So Jim, this is goes up URL, so why don't you start?
Second, a couple of questions.
Yes.
The first being, as a practical musician,
Yes.
where do you see the practical application of this theoretical concept?
So one thing that's interesting is maybe we can give this as a package to an amateur learner, right? And then they can train this model on their own computer using the instrument they have, the specific instrument. And hopefully that can help them study annotated and learn annotated music. When they play, they can see if they're playing the right notes. In certain instruments where you can go off the pitch, like the violin, maybe they can help them guide their placement and see if they're close enough to these clusters and the classification. And the fact that this can work on their own systems in real time, I think, is a big advantage. So this is just one simple application that comes to my mind. And further is audio. I think with the chord and note classification that we have now, if we start adding music concepts of rhythm, that is already done in the literature, we might be able to extend the sort of music transcription quite easily. That's another application. That's out there.
Do you see, right now we're working in pretty much the common practice tonality realm. Do you see this being extrapolated into other types of organizational systems, whether it be dodecaphonic or other types of pitch systems?
So I'm not an expert on these organizations, but my intuition is yes, if we have stable and stationary observations that my model can take advantage and create clusters out of, we can do this because one of the visitors to our lab here actually tried this model on insect classification, where we have a laser that counts the wing flaps of an insect, and they want to see if the insect is a type that can carry malaria. If so, they'll trap it. If not, they'll push the insect out to the environment so they do not impact the environment. And our problem was that the time series was too short, so we couldn't beat the SVM results. But we have shown that the model creates clusters for the wing flap rates of these insects. So I'm assuming maybe if we play those as musical notes, they might not follow the tonality of our Western music, right? So my intuition is yes, it can be extended.
Yeah, I think you have even more interesting things because you have a continuous space.
Right. Right.
You have a continuous space. So it would be nice to put the system in one space in there, you know, and see if what are the tones that you obtain, the harmonic combinations that you obtain. Because this is totally out of, you know, what we can experiment.
Actually, if we take the measurement model to our complete model, now we can generate top-down with less noise. Then maybe we can start moving the states around the cluster and see how the sound changes with certain movement within a radius. And maybe within that epsilon ball, we start hearing interesting phenomena. This is something we might be able to do this way. But I need overcomplete measurement model is needed to do this one. But it's possible. It's not out of question.
But before that, you have to solve a few problems, right? No, he's not talking about problems, right? Is there any problems on the system?
There are certain problems on the system.
So tell us about problems in the system.
We can only.
Now you are going to solve it, right?
You
don't, but how do you think?
We do know that we need a certain length of sequence for us to converge and learn from. And we have ran into this problem while working on insect classification. Those signals were about sometimes 80 milliseconds to a couple hundred milliseconds. And most of them, we were missing it. If they're like
even with the filter bank?
Because I don't know actually if you use time domain. I don't think she used time domain. But we had signals that were one window in frequency domains if I went to my frequency domain implementation. Yeah. So even with the time domain, I'm probably less than that 50 milliseconds. But we actually did not try that. So yeah. And that's one of the big bottlenecks of this model. Our model is not robust against noise. So during training, if I give, and I have experimented on this, if I give the model white noise, it forgets whatever it's learned up to that point. So because of this, we need sparsity of the observations, a certain level of sparsity of observations for the model to be able to remember what it has learned. And it can be wiped clear by presenting the model with white noise for a few time instances. So this is a big problem and possibly needs a certain constraint on learning to alleviate this problem.
I think that we are interested. I'm sorry.
I'm just going to say, and I was talking to Dr. Principe about this, one interesting outcome, I think, of the paper that you wrote for the Computer Music Journal is that as you were adding noise to the system, you were starting to see the secondary dominance pop up, which was very, in this tonal world, a very important type of relationship.
Oh, all right. So I did not know this, so maybe I need to learn a little more from you, and we can go back and experiment on that.
Yeah, but this is a very interesting thing, because we all, in the lab we are working with nonlinear inference, and here you have an example that the linear model can have wonderful properties. And now the question that is interesting is to see up to where can we, push this linear inference. That simplifies tremendously everything that we are doing with the bracket coordinate. And what are the pitfalls? And I think one of the pitfalls is exactly this, is the model as a single, your model as a single attractor state, right? And this is where, what Carmen, can do is it can create multiple attractors. And then if you have that, you'll never forget.
Right. And that's a possibility we discussed with Kant as well.
Exactly. So what I think is interesting is that looking at this from the point of view, what can we use from linear inference in more complex systems? I think we can come up with solutions that are beyond. I think that was a great stuff. Anyway, but John,
excellent. So it's very good work. These experiments that you did with the classification of notes, like you said, you did yesterday and so on. So what do you mean by that? You played it?
So
you synthetically created it?
I used the notes in the data set. So these are actual audio recordings of the trumpets playing this note, but I had the transcription of the yesterday. So I digitized that transcription and went and took sections from the recordings wherever I need. For instance, if the trumpet was to play a C, I went and picked the C from my database and created a data audio signal.
The notes. It was just one after another.
One after the other. No silence between them. If specifically there's a silence in the transcription audio, then I.
And then you trained on this trumpet notes in advance, right?
Right.
So other methods like swipe don't train.
No, they do not. So that's a really good point. They do actually give out frequencies as outputs. Yeah. We do label that this is this pattern that I have seen before. So our model needs training and does not generalize the frequencies. It labels patterns. Yeah. On the other hand, the NMF method, yin and swipe, they do give out frequencies.
Yeah. So you had to put a build classifier on top of swipe.
We just used the idea that these form clusters. So we found the cluster centers, and at each time instant, we compare our current state to all the cluster centers and label it as the closest state. Very simple.
In swipe, there's 0 free parameters, right?
Right. Swipe does not. It's only windowing of the data, and that is same overall.
Yeah. And it's like 5 lines of MATLAB code.
That's very simple.
And how many free parameters do you have?
I have the model dimensionalities of two top layers, so that's 2 parameters. I do have the noise parameters, 2, but I think with the study that we have made, we do not have to change them in a great range of values. But that's 4 of them. And then the learn parameters, if I go into the size of the model, a 60 by 60 model has just 3,600 parameters to learn in the transition matrix. So the models that numbers I learn is a lot.
So it's much more complicated.
It is. But code-wise, we are about 50 lines or so. So 5 to 50, I think we can neglect it.
It's just still more complicated.
And that's why I think we have an edge over them. I think I forgot to mention that most of the time we outperform these algorithms because of our user dynamics. They do let go of a decision earlier than we do. So they don't have enough cues in the signal to make that decision of the frequency estimation. Yeah. They just give a wrong answer.
Well, it's just each window is independent.
Exactly, each window is independent. But now I know that I'm at a cluster and my model has this Brownian motion, so it has a tendency to stay where it is. It takes me a longer time to let go of the decisions I make. Yeah. And I usually outperform the models in that period of time.
And so they would have to add a post-processing step or something to get that.
They can add a temporal network on top of their model and potentially improve their results. Same idea.
Yeah, but I mean, I think what you should also said is that this is effectively a general method for time series clustering. Right. Yeah. I mean, so this, you give the data.
More general problems.
Music, it was a use case that we chose due to its behavior, the stationarity and the clean recording design.
And a big thing with the pitch is that the fundamentals not there. You still, we're trying to match human performance, right? And it's very tricky when your fundamentals aren't there. You still get the pitch and all that, and you can just learn that, I guess.
You can just learn that. If that is a pattern I have seen, I can learn it. One thing I think in the practice talk, someone asked us, if I have a musical note and I remove the fundamental, where do you think it will be placed? And we have shown that it still is harmonically related. So I have all the rest of the harmonics. So it will be in the vicinity of the harmonic related notes, but of course it won't be in the same spot as it would have been with the fundamental in place. So that is sort of my answer. It can discover the patterns as well, even if it has not seen it. And we might have an idea of where it will be in the space, but we will not know exactly where till we play and see where the cluster is formed.
That's very good.
Dr. Hammer. Yeah, so you see your little Kalman filter doing other things, huh?
So you mentioned that. So what is really the length of a sample that you need?
So we
Does
have
it
shown.
depend on the, I guess, depends on the pitch, or
Actually, we tried in all the range of the nodes that I have, and we have shown in the time domain it's about 50 milliseconds of data on average. And in the worst case, it was about 100 milliseconds of data for me to declare a convergence and give a label. In the frequency domain, on average, it was about 400 milliseconds, and in the worst case, up to 1.5 seconds. So
you say it doesn't depend on the frequency.
it usually depends on where I was previously on the space.
Yeah, 50 milliseconds if you have, like, say, a 16 hertz thing or whatever. Like less than a cycle.
That's true. We have that. The largest frequency in our work was 5.5 kilohertz. Because of the downsampling I did to 11K, and most of the notes are in the range. The piano keyboard is, I think, up to 3.7 kilohertz, something like that. So that's why, yes, you're right. So it needs modification a bit higher in that aspect, yes.
And so also when you mentioned that you trained it on trumpet and then you use some
saxophone.
Right. So what do you mean? I mean, it identified what? The pitch or what? What did it identify?
So what I did is I knew that it had clusters for the trumpet case, right? Now, once I start playing the saxophone note, that is the pattern that has never seen, I see that the states will move and then maybe form a cluster here. And then I said, in a control case, in the classification, I make use of the label in that occasion. I say I played the note C5 and it went to this cluster. So now I associate this cluster with the C5. And I did this for all the notes in the range of the saxophone. And I see that all the clusters appear in different parts of the space, but they're still all separated. So now I can use these clusters that I discovered by presenting them to the model and observing my state and do the classification of using them. So I do not, again, give a frequency. I give a label based on my discovery property.
And did you try, like, to distinguish between, say, different instruments, to identify the instrument that is playing that particular note?
That is a question that we tried to discuss also, I think, with Matt, we discussed this a little bit. Because the idea is, I have seen all the clusters in distinct locations for trumpet and the saxophone, but they're all interlaced. So now, do I approach this problem in a case where if I say I'm near to a cluster that's a C5 of a saxophone, okay, this is the saxophone, then I can do this. But I cannot possibly find the separation surface between these where I can say this area is saxophone and this area is trumpet. Because they're all very interlaced, they're all using the same space. And I think with a linear transformation, linear model is ours, I will not be able to separate instruments from each other. I'll be able to separate the musical notes from them. But if I want that type of mapping, I might need to put a nonlinear mapping on top of it.
Yeah, but that means what? That means that the training, the speed in your space, in the state space, depends on the ratio of the harmonics, right?
Right.
So it may be that if you play the notes longer, that they will go to the same spot or not.
Because the musical note of the trumpet, let's say, has this pattern. Mm-hmm. And in the same place, the saxophone maybe has this type of organization. Mm-hmm. So even though they have the harmonics in the same place, their ratings are changed. That essentially changes the value of the states when I do the inference. So no matter what, how long I play, they'll still go to their corresponding clusters.
Okay. So that means that this is another thing where having a nonlinear model may help, right? Because you may follow the tractor and then you do that.
Yeah, because we do not have a
But everything is dependent on since it's a linear model, everything is anatomical.
We do not have invariance in terms of instruments. Or even if I take two trumpets that have a slightly different timbre, they would not have the same cluster centers. If the weightings of the harmonics slightly change, then my states all will move. The organization will alter. So this is an instrument-specific solution.
Because you did look at the sensitivity of how much it changes if you use, say, different kinds of the same, different samples of the same instrument. I mean, use different trumpets.
Yes, I
did. For piano, they have a lot of different samples you can find.
I've never trained this model on piano either because of the impulsive behavior of piano. Because piano notes come with a very strong attack and then fade out very quickly. That gives me my model a hard time because I do need more of a sustained behavior to be able to converge to my clusters. But even in the other instruments, I actually have not looked into this. How would it change with a slight move in the harmonics? We might be able to do this synthetically by altering the harmonics in my test sets slightly and start finding these epsilon models or maybe the areas that they move to. And that would be an interesting.
Yeah, because an interesting application of this would be to say check the difference between different violins. And some violins cost like $5 million a piece, and then you can buy a violin set for $10,000, and maybe you can prove electronically that is the same thing.
Is it just a label, or is there something substantially different? Yeah, that's true. I don't know how much of the timbre I can incorporate into this just by using the frequency domain. I'm not an expert on how timbre is, perceived in our auditory system. So, that if it can all be described in the frequency domain, maybe we can be able to come up with a statistical answer to that. I would need your input in terms of how the timbre reflects its properties in the frequency domain.
Yes. Any more questions?
Yeah. So can I think about, you said you have a problem with piano.
Right.
So can I think about it as your time process of trying to smooth out the result is causing you trouble here? And the simpler methods wouldn't have trouble with piano.
Yeah. No,
but because you have this Kalman smoothing process there.
So I think most of my problem when I tried the piano was the convergence time, because most of the time the note died out before my convergence time. What I do is I normalize each of my inputs. So I'll essentially be normalizing these inputs to have a similar length. And up till a point, this normalization can create stable enough inputs for my model. But most of the piano notes have died before the time scale.
The time scale is different from what your time scale you're working
for. Exactly. It's more intrinsically from the piano rather than my model. So maybe we can generalize this saying I need a sustained behavior of at least 400 milliseconds for my model to start learning this. And if this intrinsically is not possible, my model will not work in that subset of problem.
Yeah, and the piano is also, there are other things more complicated, like the use of the pedal that will change the harmonics, and so might might put up to some different point.
Absolutely. If the harmonic structure changes, it will directly go to a different point.
Yeah.
So in that case, possibly we'll have to train the model on all, like the pedal on, pedal off, or the sustained pedal on and off, and the normal scan through the model.
We have similar problems with the percussive pitched instruments like the marimba and xylophone.
I consciously made the decision of not going into those sets. That's why most of my results I have chosen woodwinds and brass instruments, because I can get a more sustained pitch out of them.
And the errors that you found in the note classifications in your system, what were they like? What kind of situations were still troubling when you had the right instruments?
So one case is where sometimes I've seen, while moving from this cluster to this, there are certain paths that my states follow. And I've seen that the states sometimes tend to slow down close to other clusters. And then in these cases, my convergence criteria might make it, if it's 4 windows long, I have a very short memory, then it can say, okay, I convert. So it goes back and labels all these with the wrong cluster. But if it had actually wait till I converge to my real cluster, it wouldn't. So my simple convergence criteria causes problems like this. In certain case is also the model. If I'm on two opposite sides of the state space, my model takes a longer time to converge. Even if it did not slow down, it just, until I get there, I already lost maybe 30% of the signal. And then once I start labeling it, it's not good enough. That's the 2% or so that we lost in the time domain implementation. And the frequency as well.
Okay. All right. There's no point for you to create. You can create a sphere in your 3D space, right? There's no point of using, just infinite dimensional. Yeah, you can create a sphere. But things that are,
Oh no, I've never used
taking
so.
solar route to Asia.
Then you did train this model on insect because of our short classification accuracy, short convergence times. She used KNN as a classification, so she kept all the training samples. Now she essentially had the idea of how the paths were shaped. So she took advantage of the fact that if I'm on this path, I'm possibly going to this node. In my experiments, I didn't do that. I just used the cluster center. I used the minimum amount of information from each cluster to classify. I can essentially keep a record of how these paths of transitions are, and then use a KNN to create exactly that sphere or that area.
Good. Questions from the audience?
Yes, Tosi.
Great job, by the way. Thank you. I was curious, I don't know if you mentioned this during the presentation, but are you able to classify different octaves?
Yes.
As separate nodes?
Right. They actually in this figure, I think you can see like here. This is nice. B3, B4, and B5 are all different clusters, and they're the same. The B nodes, and they're the different octaves.
So are you able to see a similar distance between, say, B4 and the C4 and the B3 and the C3?
I have not compared the pairwise distances and their relationship to each other. But what we have shown in the musical organization slides is that about 77% of the time, the other octaves was within the top 10 neighbors of my model. So I know that they will be in close proximity to each other. But I did not study pairwise. Anything else? Yes, Kevin.
You're just following on the recognition of differences between instruments.
Right.
Wonder if it would be a possible application to verify the authenticity of an instrument. Say, auction house make sure they've got a real scribe. Maybe you could use a model like this to verify what it is.
Intuitively, it makes sense. Because if the timbre change reflects enough on the frequency domain, then if you train this model on that particular violin, and now when you play the C5, it doesn't go to the close enough neighborhood of a C5, you can use this as a validation method.
You don't know if it's still not a valid,
Right, because they're different.
Right.
Even they're all made by Stradivarius, they sound.
Yes. I'm saying a particular Stradivarius violin.
Right, you can do
Then we train on that particular violin. But then how much of a difference does the bow create in terms of timbre? Because the bow also has a good amount of effect, right?
And also the way they hold the violin.
Right.
You could potentially use it to identify an instrument for insurance purposes. Tamper, like tamper fingerprint.
It might be a possible way of doing it, right? That would be something nice if we actually did what you suggested, try this with multiple instances of the same instrument, so multiple trumpets, and how much of a variance I do see between them. If it's enough of a variance, then it can be used as a signature.
The distance metric you need to find,
Right.
which you don't have any yet.
Is it a certain epsilon wall around the clusters? And if I reside outside that, it's not authentic enough. What are the confidence levels? Those would be the questions. And any questions? Any other questions?
All right. We have explored commercial opportunities. Thank you.